Today is our final lecture on chapters 13 and 14. Our topic today is, first of all, about amphoteric. There are some substances that act as either an acid or a base, and water happens to be one of these substances that can act either as an acid or a base, and it kind of depends on what it's with. So any species that can react as either an acid or a base is described as amphoteric. Now let's look at water functioning as a base. These reactions we've already covered earlier, but not necessarily in this context. So let's look at H2SO4 reacting with water. And this is one that we're familiar with. We know that in sulfuric acid, this would be like the first step in ionization. The hydrogen ion of the sulfuric acid will break off and be attached to the water molecule, forming the hydronium ion. And then we'll also have what was left of the sulfuric acid will be the hydrogen sulfate ion that we see over on the right. So sulfuric acid is acting like an acid, and since it's acting like an acid, that causes water to function as a base. And it's functioning as a base because sulfuric acid is a pretty strong acid. And then we see the pattern of the conjugate acids and bases over on the right side. Now let's look at a situation where water acts as an acid. So this is another one that we have looked at earlier, and this is ammonia reacting with water. And in this case, ammonia was the one that had a place for a proton to attach, so it will cause the water molecule, and it's better to think of the water molecule as being HOH at this point. One of the H up front, that hydrogen ion, will attach to the NH3, forming the NH4 that you see just to the right of the double arrows. And there's our ammonium ion. And after HOH has lost the H, what's left is the hydroxide ion that we see at the right. So in this situation, water is acting as an acid, and the ammonia is acting as the base. So a substance that acts as either an acid or a base, depending on the strength of the acid or base with which it's reacting. So in the first situation, sulfuric acid is a very strong acid, so then water will act like a base. In the next situation, ammonia is a fairly, or has a stronger base than water is, and so then water will have to act like the acid. So a substance that acts as either an acid or a base, depending on the strength of the acid or base with which it is reacting. If it's a stronger acid, as in sulfuric acid, then the substance will act as a base. Now in the second example, if however it's a stronger base than the substance will act as an acid. Now another topic that kind of finishes up the chapter is the OH in a molecule. This is not the OH in an ionic compound like sodium hydroxide. This is in a molecular substance that has covalent bonds, and molecular compounds containing this OH group can be acidic or amphoteric. And the covalently bonded OH group, not the hydroxide ion, but the OH group in an acid is referred to as the hydroxyl group. So we have a hydroxide ion like we have in ionic compounds, but if it's in a molecular compound, we call it a hydroxyl group. Now for the compound to be acidic, a water molecule must be able to attract the hydrogen atom away from that hydroxyl group. And this occurs more readily when the OH bond inside of this hydroxyl group is very polar. And all of the oxyacids that we've talked about are molecular electrolytes, and then they ionize, that contain one or more of these OH groups. So all of the oxyacids had that in there. And aqueous solutions of these molecules are acids, because the OH bond is easily broken as hydrogen gets pulled away by water molecules. In other words, water actually has a stronger attraction for that hydrogen on the end of that hydroxyl group than oxygen has on the hydrogen. So it'll pull it away, thus ionizing the molecule. So the electronegative oxygen atom draws its electron density away from the OH. Remember, in our electronegativity, oxygen has a higher electronegativity than hydrogen, and so that makes the bond polar between those two. An additional topic here at the end of our chapter is the concept of neutralization. We've dealt with it several times already, but now it just kind of put it all together. Neutralization is a reaction that produces water and salt. Remember, we gave the properties of an acid and the properties of a base, and that was always the one thing that when an acid reacts with a base or a base reacts with an acid, the two products that are formed are water and salt. So what forms as far as the salt is concerned kind of depends on how strong the acids and bases are. So we're going to start with a combo of a strong acid reacting with a strong base. And an acid-base reaction that occurs in an aqueous solution between, let's say, hydrochloric acid, which is a strong acid, and we know since it's strong it will completely ionize to produce the hydronium ion. And then we have the sodium hydroxide, which is an ionic compound, and since it's ionic, we don't say it ionizes, we say it dissociates to produce the OH negative, or the hydroxide ion. So here's our example. We have HCl dissolved in water, and we have some sodium hydroxide also dissolved in water, and we're going to pour the acid and the base together. Now in this one, it would be probably pretty easy to think of the acid and base from the Arrhenius definition. Arrhenius acid, remember, produces a hydrogen ion that we see with HCl, and NaOH produces an OH, so that makes it an Arrhenius base. And if we look at the individual pieces, the sodium hydroxide is in that aqueous solution is actually broken apart and exists as separate sodium ions and hydroxide ions. In the acid, we have something similar as well. We have the hydrogen chloride or hydrochloric acid actually existing in solution as hydronium ions and chloride ions. So in these separate beakers that we have, the first two beakers on the left, in the left one is where we have the acid, let's say, and you can see that we have the green chloride ions. We said that would be present in that solution, and we also have hydronium ions, and you can see where it's pointing to hydronium ion. The hydronium ions are the red balls with 3 hydrogen attached to it, and you can see others spread throughout that. And then we have just the regular water molecules that are just a red circle with just 2 of those blue circles attached to it. So we have hydronium ions, chloride ions, and then the water molecules. In the middle, we have a beaker that has sodium hydroxide that's been dissolved in the water, and we see the sodium ions indicated by the purple or lavender circles. They're positively charged, and if you'll notice around those we have water molecules, and notice that the water molecules have their negative side facing in. Oxygen is the more electronegative, so it's going to be facing in toward the sodium ion. And then we have the hydroxide ion, which is almost in the center of that circle. And notice it's just an O, the red circle, and one of the little blue circles attached to it. That's the hydroxide ion. So you can see others of those kind of spread throughout the solution. So in this beaker of water, we have sodium ions, hydroxide ions, and then obviously the water molecules. But when we pour the two together, you'll notice that all that remains are chloride ions and sodium ions and just water molecules. We don't see the hydronium ions any longer, or the hydroxide ions. We don't see those. If you look carefully in those circles, you don't see either any red circles with 3 dots around it, 3 little blue balls on it, or do you see the hydroxide, which is just a red circle with a single blue attached to it. So those two ions have kind of disappeared in this neutralization reaction. And if I wanted to get the sodium chloride out, as you've learned before, you have to evaporate the water to get the sodium chloride out. So you can see that over on the right there in that little evaporating or watch glass. So the overall ionic equation is shown like this. We have the first two ions, the hydronium ion and the chloride ion, and then we have the sodium ion and the hydroxide ion are in each of their separate little beakers, and when we put them together, we're going to have, we noticed in the after we poured them together, the one at the right had only sodium ions, chloride ions, and just water molecules. So because they appear on both sides of the overall ionic equation, the Na plus and the Cl negative, which are on both sides, remember those are called spectator ions. They're just watching the reaction take place. And the only participants in the actual reaction are the hydronium ions and the hydroxide ions that find each other to form the water. So if I take out the spectator ions, all I will have left is this, the hydronium ion reacting with the hydroxide ion to form a water molecule. And notice it'll form 2 of them, because if you notice on the left side I have 3 hydrogens in hydronium and 1 in hydroxide for a total of 4. So to get 4 hydrogens on the right side, I need to put a coefficient of 2 in front of the water molecule. And then I have 2 oxygens on the left, so that would make it also balanced, because that 2 coefficient in front of the water molecule means I have 2 O's. So in aqueous solutions, neutralization is the reaction of a hydronium ion and the hydroxide ion to form the water molecules. So that's what's formed in neutralization. We have the salt, but the actual, so notice that water is not the only product in that. We did have that salt. And so every neutralization reaction produces a salt. And to help you figure out what the salt is, well, look at here, it says it's a salt is an ionic compound composed of the cation from the base. Okay, so we had the base was NaOH. The cation is the positive ion, and that was sodium. So in our example here, sodium is the cation. And then we have it says the anion from the acid. That's the negative ion. So in HCl, chloride is the negative ion. So if I take, okay, and let's just kind of finish up with a review of our acid-base definitions. Arrhenius acid, by definition, was any substance that could produce a hydrogen ion or a hydronium ion. And a base was anything that could produce a hydroxide ion. In a Bronsted-Lowry definition, which is a bit broader, it has to do with protons. And an acid was a proton donor. Remember, the H in the acid is the proton. And then we have the proton acceptor was the base. Whatever substance that did that hydrogen ion attached to was now the base. It accepted that proton. And then Lewis is our broadest definition of all, and it is an electron pair acceptor. So the hydrogen ion, remember, needs some electrons, so it'll attach to something. So the hydrogen ion is actually the electron acceptor, but there were other substances that behave the same way that we looked at. And then a base is an electron pair donor, the substance that had the pair of electrons that, for instance, the hydrogen ion would like to attach to. So that brings us to the end of the last section.